We've taken a look at the single mode. Let's take a look at the differential mode. In this mode, two signals of opposite polarity, in this case out of phase, are applied to the inputs as shown in the diagram. This type of operation is also referred to as double-ended. Each input affects the outputs, as you'll see in the discussion. So we can take a look here in the diagrams. The differential inputs identified. You can see here that the inputs V1 and V2 are in fact shown as out of phase with each other. B, outputs due to just the input at V1. C, the outputs due to just the input at V2. And D, the total outputs in differential mode. So that's what we're going to be looking at. What happens when we put signals that are inverted on the inputs, treating them one at a time and then together? Well, we can see at a glance what's going to happen here. We're going to end up with inverted on the output and amplified. So in the figure B, it shows that the output signals due to the signal on input 1 acting alone as a single-ended input. Shows that the output signals due to the signal on input 2 acting alone as a single-ended input. Okay, so that was B and C. Notice that the signals on output 1 are of the same polarity. The same is true for output 2. By superimposing both output 1 signals and 2, then we get the total operation on D. And hopefully you'll get to do this in the lab. I don't know what the lab requirements are for op amps, but hopefully you'll get to see this and do this. Common mode input. One of the most important aspects then of the operation of a differential amp can be seen considering the common mode condition. And if we roll this up here, we can see the common mode configurations. Input, again, we can see in this case, both inputs are input at the same phase. Treating each one separately, we can see that the output again becomes inverted. And then D, outputs cancel when the common mode signals are applied. So output signals of equal amplitude but opposite phase cancel, producing 0 at the output. So in those cases where we have signals that we're looking at canceling and producing no signals, this becomes important. So one of the most important aspects then is this common mode condition. Any AC or DC signal that is identical on both inputs in a common mode signal, then consider the two signals as we just seen. So in each case we can see what happens, what the output looks like. In A, we have the same amplitude and frequency and phase relationship. In B, it shows the output signals due to signal only on input 1. Part C then only on input 2. Notice that parts B and C, that the signals on the output 1 are of the opposite polarity, and so are those on 2. Okay, we've already seen that. When the signals for both are applied, the outputs are superimposed and they cancel. So because they are out of phase with each other, they in fact cancel each other out. This action, called common mode rejection, its importance can be seen in a situation where an unwanted signal appears commonly on both differential amp inputs. Common mode rejection means that this unwanted signal will appear on the outputs to distort the desired signal. Common mode signals, or noise, generally are the result of the pickup of radiated energy on input lines from adjacent lines or 160 hertz power lines or some other source. So this is really good for cleaning up the signal so that you're not amplifying garbage to the output. You're able to nullify it within the common mode selection. Differential amplifiers are very efficient at rejecting low frequency common mode signals like power line interference, but they usually cannot reject high interfering signals, such as those caused by high frequency switching noise. In cases where high frequency noise is present, shielding and signal lines may be necessary. So having shielded cable takes care of high frequency noise. Common mode rejection ratio, CMRR. Desired signals appear on only one input or with opposite polarities on both input lines. The desired signals then are amplified and appear on the outputs as previously discussed. Unwanted noise or signals appearing with the same polarity on both input lines are essentially canceled by the differential amp and do not appear at the outputs. The measure of an amplifier's ability to reject common mode signals is a parameter called common mode rejection ratio, or CMRR. Ideally, a differential amplifier provides a very high gain for desired signals, single-ended or differential, and zero gain for common mode signals. Again, we want to strip off the garbage so that we're not amplifying the noise, while providing a high differential voltage gain, usually several thousand. The higher the differential gain with respect to the common mode gain, the better the performance of a differential amp in terms of rejection of common mode signals. This suggests that a good measure of the diff amp's performance in rejecting unwanted common mode signals is the ratio of the differential gain, A sub V D, to the common mode gain, ACM. So again, keep track of your variables here and their subscripts here so that you understand as you're working through the problem and properly notating the subscripts. This is what engineers do and do well. They keep track of their exact variables so that they don't become confused and everything turned to mud. This ratio is the common mode rejection ratio. So the CMRR is the ratio of the A sub V differential gain, ACM common mode gain. The higher the common mode rejection, the better. A very high value of common mode rejection means that the differential gain, A sub V, is high and the common mode gain, ACM, is low. The common mode rejection is often expressed in decimals. So we're back to using the 20 log, not the 10 log value of that ratio. Look at an example. A certain differential amplifier has a differential voltage gain of 2000. Remember, they said the numbers would be high. And a common mode gain of 0.2. Determine the common mode rejection and express it in decibels. So this is pretty easy. So we've got our two values, 2000 and 0.2. We put them into the ratio, A sub V and ACM, and we get a common mode rejection of 10,000. Expressed in decibels, 20 times the log of 10,000 gives us an 80 dB figure. A common mode rejection of 10,000, for example, means that the desired input signal, differential, is amplified 10,000 times more than the unwanted noise, the common mode, and that's a good thing. So, as an example, if the amplitudes of the differential input signal and the common mode noise are equal, the desired signal will appear on the output 10,000 times greater in amplitude than the noise. So the noise gets buried in the grass. Thus, the noise or the interference has been essentially eliminated. The example below illustrates further the idea of common mode rejection and the general signal operation of the diff amp. So in this case, we've got a diff amp that has a differential voltage gain of 2500 and a common mode rejection of 30,000. In part A, a single-ended input signal of 500 microvolts is applied. At the same time, a 100 millivolt 60 hertz common mode interference signal appears on both inputs as a result of a radiated pickup from the AC power system. Okay, that would be your 60 cycle hum. In part B, the differential inputs of 500 microvolts RMS each are applied to the inputs. The input common mode interference is the same in each part. So if we take a look at each of these, A, determine the CMRR, B, express it in decibels, determine the RMS output signal for parts A and B, determine the RMS interference signal for both. So this is a good example here where we can run through some calculations that we were just given. So the common mode rejection, the ratio of A sub V to ACM then gives us a value of about 83 hundredths here, okay? So 0.83. The common mode rejection then, calculating in dB then, 20 times the log of 30,000 gives us 89.5 dB. In C then, figure A says the differential input voltage Vn differential is the difference between the voltage on input 1 and that on input 2. Since input 2 is grounded, the voltage is 0. So voltage in differential then, the difference in V1 in and V1 and V2 in, then 500 microvolts to 0 gives us 500 microvolts. So the output signal in this case is taken on the output of 1. So V out is equal to AV differential, Vn differential. So we've just moved the terms around for solving normally for the gain. So in this case we get the gain 2500 times 500 microvolts Vn differential, or a value of 1.25 volts RMS. In B, the differential input voltage is the difference between the two opposite polarity 500 microvolt signals. So Vn differential then, again, we have our difference here, V1 to V2, and in this case we have minus 500 microvolts difference. So we'll add those together with the signs going negative, negative, positive, gives us 1000 microvolts then at the Vn differential. The output signal then voltage then V out again is our ratio for the gain V1D to V in D, 2500 to 1 microvolt then, or 2.5 volts RMS. This shows that a differential input, two opposite polarity signals, results in a gain that is double that for a single-ended input. And finally in D, the common mode input is 100 millivolts RMS. The common mode gain, ACM, is 0.083, 83 hundredths. The interference voltage on the output, therefore, is, so ACM is the voltage of the ratio of V out to V in, CM. So V out, when we move the terms around, gives us 0.083 times 100 millivolts, or 8.3 millivolts. So that was a good exercise in using those relationship and doing our conversions to decibels.